But now we are facing a complete new world of cells we want to breed and proliferate, thinking about stem cells, thinking about immunocells we want to, in no time, giving to the patient. And these are not breeded for those environments we're having in process engineering. And this is the tickling challenge, how we can overcome that and give them a comfortable surrounding that they'll multiply, that we can use them later on.
Hey, smart scientists. Welcome to another episode on the Smart Biotech Scientist podcast. Cultivating cells that are sensitive to shear stress can be challenging because the challenge is to still be able to provide enough oxygen. And I'm excited because today I'm having a conversation with Patrick Bongartz, who's the CEO of BioThrust. It's a company who has developed a Bionic Bioreactor to enable stress-free cultivation conditions to achieve higher cell concentrations and quality. Stay tuned. Are you juggling the complexities of CMC development while trying to enjoy the beauty of biotech? Have you ever wondered if there's a way to simplify bioprocessing? Welcome to the Smart Biotech Scientist podcast, where we're diving headfirst into the very challenges you face. We're breaking it down, demystifying the jargon, and giving you the keys to unlock your full potential. I'm your host, David Brohlman, and I get it. With 15 plus years in the biotech industry, I face the same challenges you do. There's a way to simplify and streamline so you can remove complexity, you can skip trials and errors, deliver without delay your groundbreaking therapy to clinics and market, and still enjoy every single step. Do you want to learn how industry experts and I did it? Grab a cup of coffee and your favorite notebook and pen. Now is the time to take your bioprocessing game to the next level. Let's smarten up biotech. Hey Patrick, welcome to the Smart Biotech Scientist podcast.
Hi David, I'm glad to be here.
Yeah, it's a pure pleasure. It's so glad to have you on the show today, Patrick. Patrick, share something that you believe about bioprocess development that most people disagree with.
That's a tough one in the very beginning. I think that the influences of fluidics are underestimated in most processes. To stretch that a bit, I think especially when we're having an eye on the design of processes and how fluidics are treated, for example, if you're having a catalyst immobilized on a surface, the fluidic control and the how to lead the fluidic through a reactor, for example, and this is true in biotechnology as in chemical process engineering, I think there's a lot of optimization possibilities. And this is true for gases, this is true for liquids. So I think there's something, if you would re-establish some industries today, like gas catalysis industries, classical electrochemical industries, but also bioreactors, we would have a complete different design of those reactors than we would have 20 or 50 or 70 years ago.
That's awesome. And before we talk about the exciting world of bioreactor design, let's talk about you, Patrick. And I'm curious, how did you get started in biotech and how did you end up where you are today, a CEO of a company?
Force science were not in my favor from the very beginning. I'm a labor class child and I got the opportunity to making the Abitur, what we call in Germany, this high school level. I did this, but before I applied for apprenticeship in Bayern, I think I never mentioned that before in somehow podcast or stuff like that. Today, I'm glad I didn't got the application. At that time, I thought, okay, that didn't work out. So I did high school, and after high school, I tried to study, and I was first one which was able to do it in my family. And I decided to study biotechnology. My father was a gardener, and I ever had an interest in those nature things, let's say that, and also the technology part. So not just the biology itself, but also to make it usable for humankind, for industry. And I was ever interested in that. And also genetics was very interesting. So I studied biotechnology. This worked out quite well. It fits my interest very good. And after my studies, after my master, I got the offer to making my PhD in chemical process engineering, so switching the field from natural science into engineering. And this was for me a complete new challenge, but also I wanted to tackle that challenge into also becoming an engineer to better understand the forces which are not just in biology, but also in process engineering. I got into that field, did my PhD for something more than 5 years. And during that time, together with my team and also Moritz, which is one of our co-founders, we invented some patents which are the fundament of the BioThrust company, what we want to may hear some later a bit more stressed out. So one thing came to another and we built up a team. We hired more people. We got a CFO, Konstantin, for the business development. And so things started very early and very tiny, but then accelerated.
Wow, what a story. And I love that I'm having a lot of conversations with scientists like you and engineers. And what I realized that often our journey is not very linear. And that's totally my story. And fun fact, I also considered doing an apprenticeship in Switzerland. It did not work out either. And it led me down a completely different path.
That's cool. Okay. When we're thinking about pupils in schools and what they're having in mind, what they can become, I think that's so limited. I think the opportunities, especially today, so wide. And if you ask the teachers, what could I become? They will maybe say teachers or policemen or firefighters. And that's all very honorable jobs, but the possibilities today are nearly endless. And I would wish that those pupils could see that from their point of view. But I think it's easier if we're having some more experience.
Yeah, and it gets much clearer as you progress in your career, a much clearer image and vision with where you want to end up. Now, Patrick, before we jump into our main topic today, I'm just curious, what do you think are the main challenges biotech scientists face when they're developing processes and then manufacture biologics?
Oh, that's a good question too. Generally speaking, this is really not to answer because each biology in each process is different, and it's quite unbelievable that this is all under one roof in biotechnology. But if you're thinking in our field and in cell applications and what we call the red biotechnology, so the biopharmacological part of the biotechnology, we are working with those cells, animal cells, for example. And these cells, they like to grow on surfaces and near to each other. When we want to make a process out of that, to cultivate more cells or to harvest the products of those cells, thinking about insulin or factor VIII for against those blood thicknesses, we have to cultivate those cells in huge masses. And they don't like that. They do not grow on top of each other. They're just growing on surfaces and they don't like that they overgrow each other. So we cultivate them on tiny carriers, for example, to expand them in volume, in a 3D volume in a bioreactor. And this scaling is a really huge issue. So this is one of the major problems we face. And I know I should say challenges, but I think this is a real problem we face in biotechnology. And there were some workarounds in the last year established. For example, you may have heard about the CHO cells, Chinese hamster ovaries, which are the backbone of nowadays biopharmacological production processes. But they were breeded to be robust against the forces we're having in classical bioreactors. And they are the backbone for producing a lot of active agents in biopharmacology. But now we are facing a complete new world of cells we want to breed and proliferate, thinking about stem cells, thinking about immunocells we want to, in no time, giving to the patient. And these are not breeded for those environments we're having in process engineering. And this is the tickling challenge, how we can overcome that and give them a comfortable surrounding that they'll multiply, that we can use them later on.
Yeah, and this leads us to the main focus of our discussion, Patrick, because designing a bioreactor for these new cell types, you mentioned stem cells, we have other cells appearing which are highly sensitive, is a huge challenge because we need to ensure stress-free cultivation. We need to ensure that we are able to grow them to high concentration. And also, if we're interested, for instance, in a recombinant protein or something, that they are at high productivity. Can you tell our listeners what are the critical factors to consider when developing a bioreactor?
Several. I think there are some nice handbooks to do so. They are all used to the, let's say, old cell lines like CHO cells. And even though they had some remarks in the last 30 years that you should have an eye on shear stress, for example, oxygen concentration in those, this was not main focus. Sterility was a bigger issue in the last decades, and they solved that quite straightforward by using always new bioreactors, so single-use bioreactors using in the industry right now, from petri dish up to several thousands of liters, where you having those plastic sacks where you filling up the very precious media, and then after the cultivation you just throw it away. But now, as mentioned, we see that the bioreactors are not designed for those sensitive cells we want to cultivate right now. There are several approaches to overcome that. For example, they try to stack the petri dish or bigger petri dish. We call this a stack. So you're having dozens or even hundreds of petri dishes on top of each other and directly next to each other. But this is just scale out. This is no real scale up. And you're still using a 2D surface. So you're missing one dimension in your scalability. And there are also those rockers, which are like, a casserole from the kitchen on a rocking device. So this casserole with the media inside is way from left to right. But also you're having huge issues when thinking about scalability. And there are big casseroles, big shaking bags like on the 500 liter or even more. But for each scale, if you want to go from half a liter to 2 liters, from 2 liters to 10 liters, and all those classical steps you have in the seed train and the scalability of a bioprocess, you need a lot of time for establishing this new rocking method for each single step. And this takes months or even years if you are in a big scale. So how we can really overcome this. And I think one of the major issues we facing is the transport or the introduction of certain amounts of oxygen in a certain level, in a certain volume. So everything is fine if you're working in 2-day cultivations with the gas transfer. Everything is fine if you're working below 500 milliliter, maybe also below 2 liters if you're using pure oxygen in the overhead of the bioreactor. But if you just start to pushing the gas through a sparger in the bioreactor, you will face the issue that the upcoming gas bubbles in a certain diameter, when they bypass the cells or the carriers where the cells live on, will induce mechanical forces, shear stress, and then the cells will disrupture, or we say disintegrate. And then, of course, you lose a lot of cells, and this is maybe an issue, but also the cells put out some signals, metabolic signals, which also influences the whole culture, because like they warn like the rest that there are some issues with the surrounding. And also if the cells do not killed or not disintegrated by the bubbles, the shear force you put on them could alter their behavior in a biological way and also their differentiation. So if you want to producing, let's say, fat tissue with stem cells, ironically, but you will get bone cells later on if you're putting too much stress on them. So this is very delicate, and you need a quite close control about the stress and also the gas transfer. Now I highlighted all the issues and how we solve that. I see that in your face, David. So we thought about how we can make this more bionic, more physiological to the cells. And we thought about, okay, how we can get the bubbles out of the reactor, but still getting the gas molecules. And this is when we came up to the idea of using a membrane bioreactor. Membrane bioreactors are also not our invention, but the art, how we do that, the crucial configuration. This is made by us, made by Moritz and myself. And we invented a stirrer for the bioreactors, what we call the artificial lung of bioreactors. Actually, it should be named artificial gills, but for marketing, we say artificial lung, and so everybody can imagine something for that. And we introduced thousands of hollow fibers from so-called ECMOs, so artificial lungs for humans in hospitals. We used that membrane and put it in a special configuration, in an architecture, like a centrifugal pump. Had a close eye on the fluidics, and we did a lot of simulations to optimize that system. This centrifugal pump made out of hollow fibers spins in the bioreactor. And by the force it induces, we mix the media and also the cells in the bioreactor, but very gently. And we know that we are way below the threshold of what is damaging the cells. And through the hollow fibers, we can induce the gas and getting the carbon dioxide as the off gas out of the system.
So in a nutshell, Patrick, you managed to overcome these mass transfer challenge with your Bionic Bioreactor. So you're able to cultivate cells at a high density while reducing the shear stress, correct?
That's true, exactly. So we decoupled mixing and gassing and induced the oxygen and carbon dioxide transfer with a gentle agitation of the stirrer. What we're seeing right now is that for CHO cells, for iPSCs, for MSC cells, so these are the new types of stem cells we want to cultivate for stem cell therapies, that they living quite good in those bioreactors. They can proliferate and the shear is no issue anymore.
Hey, smart biotech scientists. I hope you've enjoyed our conversation with Patrick Bongartz, who's the CEO of BioThrust. And in part 2 of our conversation, we are continuing our conversation about the cultivation of sensitive cells so that you can cultivate your cells in a stress-free condition to achieve higher cell concentrations and quality. Thank you very much for tuning in today. What did you think about today's episode? Please tell us by leaving a review. And perhaps you are wondering how you can develop a cost-efficient and robust manufacturing process. I know it can feel a bit overwhelming, and that's why we help scientists like you, number one, to get clarity, just to know where you need to start. We help you get confidence in a 90-day program where we walk you through the steps, all the critical steps, so that you can develop your process with confidence and with peace of mind. And finally, perhaps you have already gained clarity or you're confident. Then we help you take your business to the next level so that you can collaborate with other industry players. If one of these options is for you, I invite you to schedule a free call with us. Just use the link down in the show notes, and I'm looking forward to speaking to you on the call. All right, smart scientists. That's all for today on the Smart Biotech Scientist podcast. Thank you for tuning in and joining us on your journey to bioprocess mastery. If you enjoyed this episode, please leave a review on Apple Podcasts or your favorite podcast platform. By doing so, we can empower more scientists like you. For additional bioprocessing tips, visit us at smartbiotechscientist.com. Stay tuned for more inspiring biotech insights in our next episode. Until then, let's continue to smarten up biotech.